So in this video we'll be doing a little bit of preparation for the AP Chemistry AP exam. So this video will basically consist of the second semester content, mostly of AP Chemistry, and we'll be going over different topics such as IMFs, kinetics, equilibrium, acids and bases, applications of thermodynamics and electrochemistry. All of those topics we'll be going over in this video. All of the timestamps are in the description below, so you can skip around the video pretty easily. I'll also be including some practice below for those of you who want to practice before the AP exam. But this video is mainly going to be used as more of a summary to cover the basic big key points, just as a reminder for you before the AP test. We're not necessarily going to be going sort of in-depth on anything in this video. It's mainly just going to be about the main larger points of AP Chemistry so that you are ready for the exam tomorrow. So with that being said, the first topic that we're going to be covering is IMFs. So when we say IMFs, we're referring to intermolecular forces. So essentially, if I have one molecule here and another molecule here, these are the forces between these two molecules. We're not referring to bonding or intramolecular forces. Those are forces that are between two atoms of a molecule. These are forces that are between two molecules. And just to make sure we're understanding everything, the attractive forces between atoms in a molecule, such as covalent bonding and also ionic bonding, those forces are a lot stronger than these forces that we're going to talk about right now. And if you want to cover first semester content like bonding, there are video links in the description of other videos on our channel that go in depth on those topics. So just to start with the different types of intermolecular forces, and we'll be going from weakest to strongest here. We'll first start with LDFs, which are essentially known as London dispersion forces. So if you remember, LDFs are essentially, let's say that this molecule here has like an electron cloud around it. I'm just drawing sort of a cloud here. This cloud can easily be, like, I guess the electrons can be, there can be a momentary shift to one side of the cloud or the other by the electrons, and this creates a momentary dipole. So essentially, what can happen is that we may have a partial negative on this side because our electrons have shifted to the left due to London dispersion forces. And essentially what you need to know is that with increasing electrons, comes increasing polarizability. This is mainly just FRQ vocabulary for you to know, so that you can answer all the FRQs adequately with the proper terminology and explanation. So something may have stronger LDFs than another molecule. It will have stronger LDFs or forces because it has more electrons. Because if there are more electrons, it will be more polarizable, meaning that we'll have stronger LDFs. So that's essentially how LDFs work. Essentially, think of them as just like momentary dipoles or shifts in the electron clouds that cause a nonpolar molecule, like let's say our nonpolar molecules, we'll say like H2, F2, or O2. So if we're asking which has stronger IMFs, F2 or O2, we would say F2 because F2 has more electrons, meaning has a larger electron cloud, it's more polarizable, and it has then stronger London dispersion forces. When answering these FRQs, you need to make sure that you're mentioning aspects of what they have in common, of what each thing has in common, and why one thing has stronger forces than the other. So if we're comparing F2 and O2, we'd say both F2 and O2 exhibit LDFs, and they also exhibit London does, they both exhibit LDFs and they both are nonpolar. But F2 would have the stronger intermolecular forces because it has a larger electron cloud and it's more polarizable. So the next thing that we're going to go into would be dipole-dipole. So dipole. And this type of IMF is pretty it's pretty straightforward. Essentially, you have two molecules. Let's say I have an HCl molecule here. So we're now talking about two polar molecules. So let's say I have an HCl here. Essentially, the partial positive side of this HCl and then the partial negative side of this HCl is what's going to cause these two molecules to bond, creating an intermolecular force. So just remember, you have two polar molecules. Partial positive side of one is attracted to the partial negative side of the other, and then that's what creates that sort of attraction between them. And there's also a stronger kind of dipole-dipole IMF, and that's known as hydrogen bonding. So hydrogen bonding, I'll just say H bonding. H bonding is when we essentially have, let's say we have a molecule. I'll say, let me just draw a Lewis structure. That'll probably be easier. I'll just draw something like this. I'll say there's an H here. So this would be one molecule right here. And then I'll draw something like this. And then let's say I draw an O here. Oops. An O here. Just draw some lone pairs so it's a proper structure. And then I'll draw an H here. So H bonding is essentially when H or hydrogen bonds to FON. So that's the acronym. So FON, meaning fluorine, oxygen, or nitrogen. And only these. This is the only time H bonding. There's H bonding occurring is when H is directly bonded to one of these. And when I say bonded, we need to be careful here with our terminology. It's called H bonding, but this is a intermolecular force. So essentially, what would happen here is, let's say we had another structure here, and then here was the O here, or something like this. I'm just gonna draw some fake Lewis structure here, but this right here, this force of attraction here is between two molecules, making it an intermolecular force. When it says H bonding, and I know that can be kind of confusing, but you just need to remember that this is an intermolecular force. It's a force between molecules. Bonding is a force, attractive force between the atoms in a molecule. So we just need to make sure we're paying attention to these sort of terminologies here. And then a couple other kinds of IMFs is we have ion dipole. So ion dipole, and then this also, sorry about that, this also, I don't know what's going on with the pen. Dipole, okay, there, sorry about that. So this is essentially when we have an attractive force between a polar molecule and an ion. And this is actually stronger than H bonding, this type of intermolecular force. So let's say that I had like an H plus ion here. And then let's say I had like an HCl ion here, or this would be a polar molecule here, hence the dipole part of the name. The partial negative side, so the Cl side of this, is going to be attracted to the positive, the cation, or the H plus here, and that's how that attractive force works. Again, this is stronger than H bonding. So just to recap, we have our weakest sort of intermolecular force is LDFs, and then our next strongest is dipole-dipole, and our next strongest after that would be H bonding, and then after that we would have our ion dipole, which is stronger than H bonding. And then another sort of one that may come up is something called dipole-induced dipole. So dipole induced. Okay, this pen is I'll just do dipole-induced dipole. So essentially this is when we have an attractive force between a polar and a non-polar molecule. So essentially, let's say I have a polar molecule like HCl. Let's keep using that example. And let's say if I had a non-polar molecule like H2. Well, H2 has an electron cloud, and that electron cloud can be pulled over. Let's say I have the partial positive side here of the HCl. Well, that electron cloud can be pulled over more towards this side. There might be, the electron cloud might get pulled over here, and some electrons would be out here, but just not as many. Let's say the electron cloud gets pulled over to the left side of the H2 molecule. Now you have these electrons with an attractive force with the partial positive side of the HCl. So essentially the HCl, the partial positive side, is pulling the electron cloud of the H2 to that side so that there can be an attractive force in between there. So that's the last side of the IMFs. And another important note about the IMFs is that when you have increasing strength of your IMFs, there are some properties that are gonna also going to change. So for one, our boiling point slash melting point is going to go up, mainly because you're going to need to add more energy to break something apart, to break the intermolecular forces apart to boil or melt something. So that makes sense. Our vapor pressure is going to go down. So this is because our vapor pressure is essentially, if let's say we had a liquid here, well, our vapor pressure would be some of these particles are going to escape and turn into gas, and then that gas is going to exert a pressure, and that's vapor pressure. So if less molecules are able to escape because there are stronger IMFs holding them together, less molecules will escape, meaning that gas can't exert as much of a pressure because there are less molecules. And then lastly, there'll be solubility. So with greater IMFs, our solubility is going to go down because something is less likely to essentially become soluble or break apart in water because there are stronger IMFs holding it together. And then there are some other properties that you're probably going to want to memorize, but at the same time, these are sort of the main ones that you're going to have to worry about on the MC and FRQs. Alright, so now we'll be covering chemical kinetics. So chemical kinetics. Alright, so within chemical kinetics, so essentially what kinetics is we are measuring or studying how fast or slow a reaction occurs. So essentially, if you remember what a rate law is, let's say we have a reaction which is like x plus y goes to z plus w. Our rate law would essentially be rate rate equals K times the reaction of times the concentration of times the concentration of X, and then times the concentration of Y. And in this case, it would be 1 for both these because the coefficient in the reaction is 1. And if we add up these powers here, we have 1 and 1. This is known as a second order overall reaction. This is a second order reaction. And what that means is that these are both molarities. So essentially we're going to have molarity squared here, and then times K, and we need K to equal, we need our rate to equal molarity per second. So essentially our units of K would be, the units of K would be something like K equals, and then it would be 1 over molarity seconds, because we want to cancel out one of the molarities with this m right here would cancel, so this m squared here would become just m, and then we would get molarity over seconds to get the proper to get our proper units there. And one thing to note about this K, this is a constant for a reaction, so this is constant. And this is temperature dependent. So if our temperature is going up, then our K value for the reaction will also be increasing at the same time. And another thing another important key aspect of kinetics is the collision theory or collision model, which essentially means that if I have two molecules here, let's say I have a H2 and let's say I have an O2, for these two molecules to collide, collide and then also create a reaction, they're going to have to collide with enough energy, so they're going to have to essentially collide here first they're going to have to collide with enough energy, and that is mainly because for a reaction to occur we need to overcome our activation energy. So we're going to need to overcome the activation energy, and then these are also going to need to collide in a certain orientation for this to happen. So not going to get into sort of the orientation too much, other than the fact that you need to know that for a reaction to occur, these molecules need to collide in some sort of orientation that will allow for a reaction. And this can be depicted on a Maxwell-Boltzmann curve, essentially. So if we take our kinetic energy down here, and then we also take our our number of particles, I just put number here, and then we plot it on a curve. This will be one curve here, and then this will be another curve here. Essentially, we see that a higher number of molecules here have in our second curve here. I'll draw the second curve in another color. Our second curve here, more molecules have a higher amount of Ke, and if we draw a line here, this can be seen as like the activation energy barrier, which is essentially like the molecules need to, or the particles need to have this amount of kinetic energy to overcome the activation energy for a reaction to occur. And in this case, we would say that our second curve would have a higher temperature, meaning that it would be able to overcome this barrier compared to the first curve, which has fewer particles overcoming that activation energy barrier. And another diagram that you're going to want to understand for the AP exam is going to be a energy profile, also called like a coordination diagram. Essentially, I'll just put reaction, I'll put E for energy, E profile. file. So essentially how this works is that you have a graph here. The x-axis is going to be like the reaction coordinate. So I'll just do reaction coordinate, which is essentially just the path of the reaction as it progresses. So as the reaction progresses over time. And then the y-axis will be our potential energy. So essentially how this diagram will work for an exothermic reaction, how it will work is that our reactants will be up here, and then there'll be a curve here, and then our products will be down here. And the reason why this would be considered an exothermic reaction, meaning our delta H will be negative, is because as you can see here, our reactants are higher than our products. So when we go to calculate delta H, we're obviously doing products minus reactants, and if our reactants are higher, well, we're going to get a negative number. And then the difference for, let me just draw in white, or in another color here. I will draw an example for one that would be a endothermic reaction, and in this case, you would have your reactants here, you'd have another curve here, then your products would be up here. So we would have higher potential energy of our products than our reactants. And then this line here, or sorry, it wouldn't be that, it would be more something like from the top or from the peak of your curve down to your reactants. So if this is my reactants here, so from here to here, that right there is essentially what our activation energy is. That is our activation energy, and then from the distance from the products to the reactants, so essentially this distance right here, that would be our delta H, or our enthalpy change during the reaction. So just be able to analyze those graphs and understand what they mean for the AP test. And then with a catalyst, what a catalyst will essentially do is, here, I'll draw this in a different color here. What a catalyst will essentially do is, let's say we're looking at the white curve here. A catalyst is going to essentially move the activation energy down, so that the reaction can essentially take place faster. It's not going to change our delta H. So if I have a graph here like this, and remember this would be a exothermic graph. This distance from the peak to the reactants, that is our activation energy, and that is going to actually be lowered. So if we add a catalyst, the graph would look something more like that. There'd be less of a distance between the peak and the reactants. But this distance right here from the reactants to the products, that's not changing at all. So a catalyst does not change the delta H, it only changes the activation energy. So now we'll be going into more rate law stuff. So our integrated rate laws, essentially for these, what you need to know is that if you have a graph here and you're plotting the concentration, I'll just put this bracket for concentration versus time, and you have a straight line here, that essentially means that it wouldn't be like this, because over the course of reaction the concentration would be going down because we're using up more of the more of the reactants. It'd be going down like that. If you have a graph like that, that means you have a 0th order reaction. So you can put 0th order, and the equation for this would essentially be the concentration. This is all on the equations sheet, by the way, so I actually won't write this down because you'll have access to this during the AP exam. Just remember that on the equation sheet, it goes 0th first and then 2nd order is what they give you for your equation sheet. So then another graph would be here, and if we have a straight line like going like this again, but this time we have the natural log natural log of our concentration versus time, and it gives us a straight line. That means that we have a first order reaction. So this would be first order. And then the third kind of graph would be if we have something like 1 over the concentration. So 1 over, I'll put the brackets here for concentration. So 1 over the concentration versus time. And then this would give us a straight line that looks something like that. So essentially be able to understand and look at the different graphs of the integrated rate laws, and be able to look at the x and y axis to identify which sort of order it is. And then another equation that it's going to give you on the equation sheet, but you should know, is the half-life. So essentially T1/2 equals 0.6993 over the constant, our rate constant. It's okay. That's essentially how long it takes for half of the species to be used up, like how much time that takes. And then just to quickly review what our rate laws look like in terms of determining the order of things. Let's say I have the concentration of A, and then I have the rate of the reaction. Let's say the concentration of A is 0.5, and the rate is, I'll say 1 times 10 to the, 10 to the negative fifth, something like that. And let's say A doubles, so A goes to 0.1, or sorry, not 0.1, A would go to 1. So let's say A goes to 1, A goes to 1, and then our rate also doubles. So 2 times 10 to the negative fifth. Well, that essentially means that now that A is first order, because we've doubled here, and then we've also doubled here. And one important thing to note, this is all while our our other reactant here is staying constant. So essentially it's going to give you a table. Just look at what's changing from different trials of the experiment, and then determine what is staying constant and then what is changing, and then how is that affecting the rate. Now if this was multiplied by let's say 3, and this was multiplied by let's say 27, well then A would be third order, because we would say 3 to the n equals 27, and n is equal to 3. So essentially that would mean that we are at third order. Similarly, if we said that the rate was multiplied by 9 and then the concentration was multiplied by 3, that would mean that we would have a second order for A. And then to find the overall order of it, we would simply add up the orders of A and B to find the overall reaction. And then so lastly I want to get into is reaction mechanisms. So this is also pretty simple. Essentially we're just looking for one thing, and that is the slow step. And usually rate laws cannot be simply found by looking at the coefficients in the equation. It's usually given to you or determined experimentally. So essentially what would happen here is, let's say that we had like O3, so we had O3 gas, and let's say that this went to O2 and O. I'll just say this is gas as well. So essentially and then this would be denoted as our slow step. So from here we can write a rate constant. We can say that our rate is equal to K times the concentration of O3. And then if O3 had a 2 in front of it, we'd add a 2 here. We can only do this and write the rate constant from this expression because this is considered an elementary step, or a step that essentially is like just one part of the reaction as a whole, one part of the mechanism. And if we had, occasionally you'll find, let's say I have a reaction here, and let's say the products of this reaction is like, I don't know, NOBr, something like that. And then we use NOBr over here on this side, and then let's say this is the fast step. This is a fast step. So essentially this is not our rate determining step. Let's say this is the slow step. Slow step. So that's our slow step there. Essentially, because we have a reversible reaction here, let's say that this was just let's just say that this was just NO plus Br here. Well, we can essentially say that now this, we can substitute this for this over here in our rate law, because this is a reversible reaction here. So if we were going to use NOBr and we were going to say is NOBr plus A goes to something that's not relevant to the problem, we can just say that our rate is equal to our K times the concentration of NO times the concentration of Br, and then times the concentration of A. Because remember, we've essentially substituted this part for NOBr, because our first step was fast and our second step was slow, and we're only looking at the slow step as a rate determining step. So that's everything we needed to go over for kinetics. Alright, so now we'll be discussing chemical, in this part of the video we'll be discussing chemical equilibrium. So this is, this part of the unit, this part of the curriculum is pretty short in that there's not a lot of hard concepts, it's more just logic based. So essentially, chemical equilibrium is basically rooted in the fact that we have these things called reversible reactions. So A plus B goes to C plus D, and essentially what these double arrows mean is that this reaction is reversible. So when we've reached equilibrium, we are saying that the rate of the forward reaction is equal to the rate of the reverse reaction here. We're not saying that the concentrations of A and B are necessarily the same as C and D. We're just saying the rate of the reactions are the same. So now going into what our equilibrium expressions look like. Let's say we have A plus B, and then goes to C plus D. Remember, these expressions only apply if we have a reversible reaction here, meaning we are going to reach equilibrium at some point. So essentially what our equilibrium expression looks like is we would say K and then equilibrium is equal to our products over reactants. So it'd be essentially C, concentration of C over concentration of D, over concentration of A times concentration of B. And these powers here, in this case it would all be 1, are determined by the coefficients here. So as we can see, this arrow would actually go here. C has a coefficient of 1, therefore the power of C is 1 in the equilibrium expression. So another type of equilibrium expression that we use is known as our Kp. This is essentially for gases. So it's the same concept. We would have instead of concentrations, because we don't use concentrations for gases, we use partial pressures. We'd have the pressure of C times the pressure of D over the pressure of A times the pressure of B, and these are essentially partial pressures. And in the same way, let's say B, so let's say we had 2B, well, the partial pressure of B would be raised to the second power in the expression. And then one really important thing to remember about these is that pure solids, so solids, and liquids are not included. That's very important to note, that you shouldn't be including anything that's denoted with an S or an L in your equilibrium expression, because those don't contribute to equilibrium like aqueous solutions and gases do. So another type of equilibrium expression is Q, which is known as the reactant quotient. And essentially we use Q when we are not at equilibrium and we're just given the concentrations or pressures of our species, which are either gas or in the gas or aqueous form. And essentially we calculate it in the same way, where Q would be equal to, if we're just using the reaction from above, it'd be concentration of C times concentration of D times concentration of A times concentration of B. So it's essentially the same sort of calculation, but in this case we are not at equilibrium, so we're using Q when we're not at equilibrium. So let's go into comparing Q to K. So if we're saying Q is greater than K, well, that essentially means that we have more product than we do at equilibrium, because remember, if it's products over reactants, so if our product increases, then our Q increases. So to reach equilibrium again, we're going to say that our reaction is going to shift to our reactants, meaning that we're going to go from our products to reactants. So we're going to use some of our products to create more reactants so that we can reestablish that equilibrium. Similarly, if we say Q is less than K, well, now we have more reactants than we do at equilibrium. So to reestablish equilibrium, essentially we're going to compensate for that, and we're going to say we're going to shift to products. So that's essentially how Q works and how we compare Q to K. And then, one other thing is that if Q is equal to K, that simply means that we're at equilibrium. We're at equilibrium. So if you calculate a Q value and it's equal to the K value they give you, that means that the reaction is or the process is already at equilibrium. And then one other thing to mention, you probably already knew this, but up here is that a large K means that we are obviously product favored, because it's product over reactants, and the more product we have, the higher the K value. So I'll just say product favored, and then a small k would essentially mean we are reactant favored. So pretty basic stuff here, simply just like a lot of plugging in and stuff like that. But there are times where you may have to use something called an ice table. I'm sure we remember how to use an ice table. Essentially, let's say it's given you this right here, this reaction. Essentially how you would do an ice table, let's say it gives you 0.1 molar of A, so 0.1, and let's say it gives you 0.1 molar of B, and let's say we're starting with no C or D. Essentially how we would calculate the K value for this is, or for this example, they would give you a K value. Let's say they give you a K value of like 4. So this is just an example. I don't know if this is actually going to work out, but essentially you do minus x here, minus x here, and then minus x here. So then our equilibrium would be 0.1 minus x for both of these. And let's say we had, let's make this a little more, let's say we had 2c. Well, we're going to start with 0 for both these, but we're going to add 2x only because our coefficient in the reaction is 2. So then here we would add x because our coefficient is 1. So we would have 2x, and then we'd also have x here as our equilibrium. And then essentially what we would do is we would say products over reactants, so 2x, and then times x, and then over 0.1 minus x. And honestly, the best way to solve these is I don't personally do the math or the algebra. I just simply plug in both of these sides to a graphing calculator and then find the point of intersection, and that will give you the value for x, and then you can answer the question accordingly. So now we'll go over to Le Chatelier's principle, which is essentially like applying different stresses to a system that is at equilibrium. So let's just use our classic a plus b, then this will go to c plus d. So essentially what will happen here, let's say that we increase a. Where's our reaction shifting? Well, we're increasing a, meaning we have excess a that we need to get rid of. So to reestablish equilibrium, we're going to shift right, meaning we're going to produce more products because we want to get rid of some of that extra a. So let's say that we decrease c. Well, again, we're going to have to shift to the right so that we can compensate for the decrease in c by making more of it. So again, shift, I'll just put here shift to the right. And then let's say that this is an exothermic reaction. So we'll say delta H is negative. So what essentially this means is that if our delta H is negative, we're going to be adding energy on this side. So let's say our temperature goes up. Well, because our temperature has gone up, we're going to need to get rid of this excess energy or heat over here and transfer it to the other side to reestablish equilibrium. So for increasing our temperature, that means essentially we're going to shift to the left to get rid of that sort of excess energy or heat there. So that's like sort of how our stresses work. Now, if these were gases, let's say we do plus E here, we'll add another molecule on the right side, or another species. Let's say we increased our pressure, which would also be known as decreasing our volume, because remember, pressure and volume are like proportional to each other. So, they're inversely proportional. So when we decrease the volume, we're increasing the pressure, and when we increase the volume, we're decreasing the pressure. Because we have more moles of gas on the right side, increasing the pressure means that we would have to shift to the side with less moles of gas, because we want to lower the pressure now to reestablish equilibrium. So that means we would essentially shift to the left. And that is sort of it for our equilibrium. So now I want to go over and do some solubility. So solubility is pretty basic. Essentially, let's say we have let's say we have the element A, or not the element, the solution AX, and we're dissociating it into A plus and X minus. Let's say we're doing that. So essentially what the equilibrium constant tells us is that is this going to either break apart? So this is a solid. Is this either going to break apart, or is this going to dissociate into its ions? So essentially the KSP would be equal to KSP equals the products of the it would be the product of the concentration of the A plus and X minus. And this would essentially be this would be our KSP expression. In a similar way, we can use Q for this if we're not at equilibrium. So we can say QSP, and if QSP is greater than KSP, that essentially means that we're forming a precipitate. So precipitate would form. I forgot to include here. So precipitate would form. This is also a reversible reaction. So if our Q is greater than our KSP, then a precipitate would form. Similarly to how we compared Q and K earlier, if our Q is less than K, that would mean no precipitate forms. So no, I'll just write no form. So no precipitate will form if our Q is less than K. And sorry, this should actually be flipped. So this reaction should be flipped. It should be written the other way around. So you would essentially have your two ions, and then they'd be forming into the solid over here. So that's essentially everything we have for our equilibrium unit. Alright, so in this part of the video, we'll be going over applications of thermodynamics. So this was essentially thermo part 2. And basically what we did is in this unit we covered entropy. So entropy, or also known as the letter S, is essentially like the dispersal of energy in a system at a given temperature. So how much energy is dispersed in a system at a given temperature. Now, entropy can be represented as delta S for change in entropy in a system, and essentially this is like any other delta equation that we've done before, like for example delta H or enthalpy. This is essentially the entropy of the products and then minus the entropy of reactants. So pretty basic stuff here. So here are some ways that our entropy can increase. So entropy would increase when we're changing phases. So for example, if we go from a solid to a liquid, that would be an increase in entropy. If we go from a liquid to a gas, that would also be an increase in entropy. And this is mainly because we have, one could say that we have more chaos in these phases than we do in the other ones. Also, another way that entropy can increase would be if you have more molecules than in the products than you did in the reactants. For example, if we have a reaction where it's like A plus B goes to let's say 2C plus 2D. Well, on this side we have 2 molecules, on this side we have 4 molecules. Therefore, our entropy is going to increase. And so for going back to delta S is the standard entropy. So we would denote this by saying entropy with this little knot here of the products minus the standard entropy of the reactants. And essentially the standard entropy of a uncombined element or a pure element, for example H2 or hydrogen gas, is not actually going to be 0 like it is for delta H. It's actually going to have its own value. So just keep that in mind, is that these pure elements do have entropy values. So now let's get into the different formulas that we're going to go over. So essentially delta G represents our Gibbs free energy, which is essentially the energy that is available to do work in the reaction. And reminder, when we're talking about Gibbs free energy and delta G, we want to be at standard conditions, meaning that all gases are at 1 atm and all solutions are at 1 molar, and we are at 298 Kelvin. So standard temperature and standard concentrations for our species. So essentially, as we know, if delta G is less than 0, then this is, I'll put TFP, which means it'd be thermodynamically TFP, thermodynamically favorable process. And then if delta G is greater than 0, then we have it's not a thermodynamically favored process. So there are a couple different equations we can use to determine delta G. One of them being delta G is equal to delta H minus T delta S, and then T is equal to temperature in Kelvin. And then our delta H is also obviously our enthalpy, and our delta S is our entropy. Now, one little chart that I like to use, and what the AP exam and a lot of our practice questions will ask is this reaction favorable at high temperatures, low temperatures, or all temperatures? Essentially what I like to do here is I like to go here, and I'll do delta H here. I like to make this little chart, delta S here, and then you have, is this a thermodynamically favored process? So if our delta H is negative, meaning we have an exothermic reaction, and our delta S is positive, that means we're thermodynamically favored at all temps. So no matter what temperature it is, we will be thermodynamically favorable, meaning delta G will be negative. But an alternative to using this sort of chart I'm making here is to just simply do the math. But this chart is sort of a quick way for you to get around those questions which ask, is this reaction favorable at high temps, low temps, or all temps? So let's say our process is endothermic, and our entropy is going down. So let's say delta S is negative. Well, this would be favored at no temps, because for a reaction to be favorable, we're either going to have an exothermic reaction, or entropy is going to have to be increasing. The reason being is that for the reaction to have a negative delta G, meaning it's spontaneous, we're going to need to have our system produce some heat instead of us adding heat to the system, because then obviously it wouldn't be a spontaneous reaction if we're adding heat to the system. And like we discussed before, when entropy is going up, that means that we're becoming more favorable. And then what I like to do here is, now what you have left is high temps and low temps. Just think of it this way: low temp means negative, so essentially our delta S and delta H are going to be both negative, and high temps mean positive, meaning both of these are going to be positive. So this is sort of just an easy way for you to get around those type of questions. And then real quick, some other formulas just as a reminder. We have delta G is equal to negative RT natural log of K, where K is our essentially our equilibrium constant. So essentially it would be when we take the products concentrations over the reactants concentrations, and then we have R, which is our gas constant, which in most cases will be 0.08206, and then we have T, which is obviously our temperature. And I want to remind you that when we use this equation, all of our gases that we start with, or all of our species or whatever it is, need to be at 1 atm or 1 molar, and then our temperature is also going to need to be at 298 Kelvin for this to work. We need to be at standard conditions to use this equation. Okay, and then the next thing that we're going to go over is what is driving our reaction to be thermodynamically favorable. So I'm going to go back to this chart up here. Essentially, for a reaction to be thermodynamically favorable, we're going to need either delta S to be positive or delta H to be negative, because as you can see here is when delta H is positive and when delta S is negative, we are not favorable at any temperature, no matter what the temperature is. So one of these is going to have to fit our requirements to be a thermodynamically favored process. And one of the questions that comes up often is, what is driving the reaction? Is it enthalpy or is it entropy? Well, let's say we have a reaction. Let's just say that we have A plus B, and then that goes to C plus D. Okay, let's say the delta H for this reaction is negative 25 kilojoules per mole. So let's say the delta S for this reaction is, we'll say that delta S is, we'll just say that delta S is negative as well. So what they'll ask is, what is driving the reaction? Is it enthalpy and entropy? So I'll put nth and entropy. Is it only, instead of putting enthalpy, I'll put delta H. Is it only delta H, or is it only delta S? So what it will ask is, what is driving the reaction? And as we know, what drives a process to be thermodynamically favored is an exothermic reaction, and then also increasing delta H. So in this case, we have a negative delta S here, so it's not being driven by entropy. And then we also have a negative delta H, meaning we are exothermic. So we are being driven by enthalpy, not entropy in this case. So it would be, so number 2 would be the correct answer for that. And one more concept we need to go over is that let's say that we have an element which is like element A, and it's in a solid form, and then we're going to 2A and then in the gas form. Now, one would say that this reaction has increasing entropy, but at the same time, so it would ask, is delta G for, so actually no, it would probably ask something like delta G is negative, but the reaction is not occurring. So why is this happening? Well, the main reason when we see something like this is when A is in something we like to call kinetic control, and that essentially means that we have a really high activation energy. So we have a very high activation energy, meaning that at that temperature, a lot of energy needs to be added to the system to essentially catalyze it to get the reaction going. So basically, if our delta G is negative but the reaction is not occurring, that usually means that we have a very high activation energy that we need to overcome, which is stopping the reaction from happening. And then one last thing that I want to go over real quick is that we essentially, let's say we have multiple reactions. We have A plus B goes to C plus D, and then we have X plus Y goes to Z plus, I don't know, we'll say Z plus C or something like that. Anyways, it doesn't matter. Let's say we have a delta G value here and a delta G value here. Well, this is simply just Hess's law. To get the delta G for the reaction, we're just going to add both these up to get the overall delta G for the reaction. And that's sort of everything you're going to need to know for the applications of thermo unit.
Let's get into electrochemistry. One of the first topics covered in electrochemistry is entropy, which is a measurement of the disorder in a system. So the greater the disorder is, the greater the entropy is. So for example, a liquid would have a greater entropy than a solid, and a gas would have greater entropy than a liquid and a solid. And so it's represented by S, the symbol S, and it's like delta H at standard conditions, as standard entropy is S with the symbol. That's at 25 Celsius. The change in delta S is just like delta H again. It's the sum of the S in the products. Subtract that with the sum of S in the reactants, and that's your delta S. Gibbs free energy is another concept we learned. The delta is symbolized with delta G, and so it determines if a process is thermodynamically favorable or unfavored, or if it's, in other words, spontaneous or non-spontaneous. And so, the delta G is calculated the same way as delta S or delta H. So sum of the G in the products minus the sum of the G in the reactants. If G is negative, that means it's thermodynamically favored. If it's positive, that means it's not thermodynamically favored. And if it's 0, that means we're at equilibrium. A thermodynamically favored process results in decreasing enthalpy, increasing entropy, or both. This is seen in the equation delta G equals delta H minus the temperature times entropy, or change in entropy. So T is our temperature in Kelvin. Delta S is given in joules over moles times Kelvin usually, but you got to convert it into kilojoules per mole times Kelvin because delta H and delta G are measured in kilojoules. Gibbs free energy can also be calculated if you know the equilibrium constant K, with delta G equaling negative RT times the natural log of K. R is our gas constant, which we've done stuff with in gas units. T again is temperature in Kelvin, and K is the equilibrium constant. If delta G is negative, that means our K value is greater than 1 and the products are favored at equilibrium. And if delta G is positive, that means K is less than 1 and the reactants are favored at equilibrium. Here's an image of a galvanic cell. And so in a galvanic cell, well, first off, we're talking about half reactions, the oxidation and reduction reactions, which we did, which were covered earlier. But each half reaction has electric potential. Potentials are given as a reduction half reaction. And so if you flip the reaction, flip the sign in the oxidation potential. Galvanic cells use favored redox reactions to generate current. Two half reactions happen in separate chambers as seen in the image here. And the electrons from the oxidation pass to the reduction reaction, which then creates the current. Oxidation takes place at the anode electrode, and the reduction takes place at the cathode electrode. And the salt bridge, also seen here, keeps electrical neutrality. So without the salt bridge, the voltage would be 0. This is just what I was just talking about. So voltage and favorability. So the redox is favored if the potential has a positive value. And so the reaction potential can be calculated using Gibbs free energy with the equation delta G equals N times Fe. N is the number of moles in the reaction once you balance the two half reactions. F is Faraday's constant, seen here, and E is your standard reduction potential. If E is positive, that means delta G is negative and it's not thermodynamically favorable. But if E is negative, that means delta G is positive and it is not thermodynamically favorable.